All right, let's talk about the 2 degree of freedom mechanism problem using VirtualWork. So we're going to look at a fairly simple version of this. We're going to look at a double slider. So we're going to have 2 sliders, and they're going to be connected by a spring that's pinned to each of those sliders. Okay, and so what this is going to look like is that spring is going to allow those 2 sliders to move independently of each other. And so we can draw a vector loop associated with that. That's just going to be something like that. And that's where the pins are there. We can call this one R1, this one R2, and this one R3. All right, now just the kinematics of this, we're going to have a position equation, a vector equation that looks like R1 plus R2 equals R3. And we can observe that theta 1 equals 0 degrees and theta 3 equals 90 degrees. And so when we do the next part, we can write R1 e to the I theta 1 plus R2 e to the I theta 2 equals R3 e to the I theta 3. And we can substitute in for theta 1 and theta 3, and that will give us e to the I 0 is just 1, and so we'll have R1 plus R2 e to the I theta 2 equals R3, and e to the I 90 is just equal to I, so that will be our complex number equation for that vector loop. Now, if we think about what changes with time on this one, R1 changes, R2 changes, theta 2 changes, and R3 changes. Okay, so we can solve for 2 unknowns, which means we have to be given 2 of them. This is a 2 degree of freedom system. As I said, the sliders can move independently. So what's that's going to tell us is our Q1 and Q2, we're going to have two coordinates, and they're going to be R1 and R3. Okay. Now, if we were going to do virtual work on this, we have to have some input and output forces, and so we can have, say, an input F1 right here, and then why don't we have a resisting force F3 up on that slider. Okay, so we're going to assume that the motion is going with F1 and that it's being resisted by the force. So this is our Fin, and this is going to be our F out. Okay, now they really could move independently of each other, and both of them, the sliders can both be moving in the direction of the forces indicated. It really depends on the stiffness of the spring. And so hopefully those equations will show us how that's going to go. Now, our virtual work equation, virtual work is going to look like F dot dz, and so that's a sum for all our forces, plus dv dq dq. Okay, and so this force, or the dz, has to be ideally in the direction of the force, and we've got some that work very nicely for that. And so what we're going to have for this equation, and this will of course be equal to 0 at equilibrium, and so we have F1 and R1 is exactly in the direction of F1, so F1 dot dr1 works, and then we also have F3 dot dr3, and then we'll have, excuse me, that should be a minus right there, minus dv dq, and so we're going to need an expression for the potential energy in the spring. Let me just leave it as dv dqi dq, and that's going to be equal to 0. Now, important thing on this is that the motions of R1 and R3 are independent of each other, but the motions of R2 is not. Okay, so let's take a look at what that potential energy of that spring looks like. That V is going to be 1/2 K, and then it's going to be R2 minus R2 naught, where R2 naught is the undeflected length of that spring, and that's going to be squared. Okay, and so now we've got two different Q's, and they actually are going to show up in different expressions. Okay, or well, that'll give us two different equations. Okay, so we're going to have the partial of V with respect to R1 is just going to be equal to 1, I guess, sorry, the 2 will come down here, and so we'll just have K R2 minus R2 naught, and then we'll have dr2 dr1, and that's just going to be a kinematic coefficient, and then we'll also have dv dr3, which is our other independent variable, and that'll give us K R2 minus R2 naught, which you can think of as the force in the spring, and then it's going to be multiplied by kinematic coefficient, which in this case actually should be partial derivatives, dr2 dr3. Okay, so that gives us the question of what the partial of R2 with respect to R3 is. Okay, and so what we do for that is we go back to our kinematic equation, and we have R1 plus R2 e to the I theta 2 equals R3 I. Now, all these things change, and so the first kinematic coefficient we need is a partial with respect to R1. Okay, and so we're going to take the derivative, partial derivative of this equation with respect to R1. Okay, and so the first thing we get is dr1 plus we'll have dr2 dr1 e to the I theta 2, and then we'll get an R2 d theta 2 dr1 I e to the I theta 2 equals dr3 dr1 I. Now, there's a lot of stuff going on there, and actually a few things that we just have to know how they work. Okay, the partial of R1 with respect to R1 is just 1. Okay. dr2 dr1 is a kinematic coefficient that we need to solve for. And so that's going to be what we're going to be looking for from this equation. We'll have R2 d theta 2 dr1 I e to the I theta 2. Now this is another kinematic coefficient that we could solve for, but it doesn't actually show up in our virtual work equation, so we don't actually need it. The last thing we have is this partial derivative of R3 with respect to R1. And this is important when you have 2 degree of freedom problems. If you're independently controlling those two inputs, the associated with R3 and R1, the partial derivative there is by definition 0. Okay? So we now have a complex number equation with 2 unknowns, and we know how to solve those. Okay? And so we'll pick that up in the next video.